everybody, and welcome to Trilogy Tech Talks. My name's Jeffries. I'm your host. We appreciate you all for joining us, of course. Today, we got a really exciting discussion. We're going to be talking KSQL, streaming SQL for Apache Kafka with our friends at Confluent. So if you're new and joining us for the first time, I'll give you a little bit background on Tech Talks. We've created Tech Talks as a way to bring together the community. So Trilogy, our partners, and any technologist really in the community that's interested in learning about these topics or just taking deeper dives into them. So really, again, it's about bringing the community together in general so we can better serve our clients and have a better understanding for our industry as a whole. So Trilogy and Confluent obviously have a service partnership, but we decided to bring this knowledge to the public as a way to not only showcase our technical expertise, but also as a way to help better understand the benefits of cloud computing, and more specifically for our larger clients that are managing large amounts of data. So this is very much an open discussion. Your questions are more than welcome. We want this to be kind of interactive. While you can't turn your cameras on, you can obviously utilize the chat function. We have the Trilogy Confluent series hashtag on Twitter. So we'll be viewing that as we're going along and managing any of your questions there. So feel free to use anything you'd like. And we'll go from there. So now, joining us all the way from San Francisco is Derek Nelson. He's currently a senior product manager for Confluent. He's been working with them for about 2 years as a KSQL product manager. So prior to joining Confluent, Derek actually co-founded and was the CEO of a startup called PipelineDB. And PipelineDB is a time series data analytics extension for PostgreSQL. And that was later acquired by Confluent. So hence why he is there. So anyway, I want to kick it off to Derek. Thank you all again for joining us. And thanks so much, Derek. Thanks so much for joining us and welcome.
Thanks, Chad. And thanks for organizing this session. Happy to be here with you all. So what this talk is going to cover is sort of the high-level background behind why we built ksqlDB in the first place, and then we'll progressively drill into more detail as we go on, getting into specific features that I think are unique to ksqlDB and interesting to most users. And then at the end, we'll go through a couple of simple example use cases. So this is a high-level agenda we're going to follow. As I mentioned, we'll begin with just a quick bit of background on why we built ksqlDB in the first place, because I think that contextualizes a lot of the design and architectural decisions that we've made. After that, we'll get into a high-level overview of some of the key unique features offered by ksqlDB. And then we're going to go into a relatively brief introduction into the high-level ksqlDB architecture with some visualizations about how the internals work in terms of continuous query processing. And then, as I mentioned, we'll end with a few simple use case examples just to frame all of this with some concrete workloads. And then whatever time is left, we can use for questions, comments, general discussion. There should be plenty of time for that. So if you have any questions, please feel free to ask us at the end.
Great. Derek, I'm going to just jump in real quick. It looks like there was just an issue with the actual live. So it started right as you were talking. So I just want to overview real quick
Sure.
What's going on. So again, everyone, this is Derek Nelson. He's joining us from San Francisco Bay Area. He's a staff product manager right now for Confluent. Been working with them for about 2 years as a KSQL product manager. And prior to joining Confluent, Derek was actually a CEO and co-founder of a startup called PipelineDB, which is a time series data analytics extension for PostgreSQL that was later acquired by Confluent. So anyway, this is the third part in the series. If everybody wants to go back and watch, this is kind of stacked information, if you will. So everybody, welcome. Thank you so much for your time today. And Derek, I'll hand it back over to you, man. Just wanted to cover that real quick.
Okay, great. Thanks, Chad. Should we keep moving from here, or would you like me to go?
Just keep moving from here. You're good. Yeah.
Okay, cool. Let's go ahead and start with the background and motivation. So I think some of this will be a review for you guys, but as I said, I think it's important to understand why we built ksqlDB in the first place in order to contextualize a lot of the things I'm going to discuss, but we'll try to keep it relatively quick. So this is what a lot of large enterprise data infrastructures looked like before Kafka. You had this huge conglomeration of different independent services. If one service wanted to use the data of another service, that typically required a point-to-point connection with that service, causing an exponential growth in the number of point-to-point connections, and also in general complexity as the number of services grew in the enterprise. So this is obviously undesirable for a number of reasons. It's inefficient network-wise. It's hard to roll out new services and ultimately innovate quickly when you have an infrastructure that looks like this. So what Kafka did, you could replace the Confluent section in here with Kafka as well. What it did was it created a centralized message bus that all of these different services and clients and APIs could communicate directly with, rather than having to communicate directly with one another. So this simplified large enterprise infrastructures substantially. And that was one of the key innovations of Kafka. It really consolidated large complex infrastructures. But the idea, or the problem of moving data around, shuffling data between services, APIs, and clients, as Kafka does, that at this point is largely a solved problem. I think it works really, really well. But it's also important to keep in mind that that's not all any users are doing with that data in Kafka. All of the data, all of the value that they're deriving from that data that it's stored and managed by Kafka is extracted using some other means, whether it's producers, consumers. So when companies are looking to understand where they can use stream processing technology to simplify their architecture, I always advise them to look at what their producer and consumer code is doing, because in a lot of cases, whatever's happening in the producer before a message gets written to Kafka, or within a consumer after a message gets read from Kafka, in many, many cases, these consumers and producers and what's happening before and after them is actually a rudimentary form of stream processing. So again, I encourage everyone to take a look and understand at what your producer and consumer code is doing, to try to understand if you could actually leverage stream processing technology to do those things for you. And with all the companies and users that we've worked with, not just at Confluent, but even before Confluent with Kafka, that gave us an opportunity to really understand what businesses are doing with their data, what problems they're solving, and ultimately what things are common across many different users that could be easily solved by an off-the-shelf product that serves that purpose directly, rather than requiring any new complex application code leveraging producers and consumers. So that's largely what we aim to accomplish with our stream processing technology, is solving a lot of those really common data processing problems that a lot of companies are having to solve with home-baked solutions. And rather than relying on home-baked solutions, you can now just use an off-the-shelf product that's battle-hardened, feature-rich, designed by brilliant engineers to solve those problems for you, so that you can ultimately focus on your business's core competency. And so one slide I always like to share here is the question of what is stream processing in general. And I think one good perspective to take here is that there are three fundamental models of data processing that we see. These actually roughly follow the evolution of data infrastructure over time, moving from left to right. So the simplest data processing model is the request response model. I think web, HTTP, traditional databases are good examples of this, where a client issues a request to some system, whether it's a web server or a database, and they get back one response. So it's largely transactional, largely stateless, very straightforward, and still extremely useful in a wide variety of use cases. And then the next major shift in data processing technology came with batch processing. And examples of batch processing would be things like Hadoop, MapReduce, periodic ETL jobs that companies are writing themselves and running every hour or every day, and so forth. But the fundamental thing about data processing is that you have some large silo of data, you execute some processing over that data that typically takes a long time to return, and then it returns a result whenever it's finished, whether that be minutes, hours, or days. And then the current shift that's happening in the data infrastructure industry has ushered in stream processing. So stream processing is much like batch processing, except that you don't have to wait for results to be returned when the batch processing job is done. So instead, stream processing jobs continuously process data, whether it's in Kafka or some other system, and it produces real-time incremental results as it's running. So in a lot of ways, you could think of stream processing as batch processing, except if the batch processing job was continuously emitting output every time the output changed. So that's how we kind of think about stream processing. And within that bucket of the stream processing model, what types of approaches can you use to perform stream processing with Confluent's platform? And there are three clear ways to do this. And as you'll see in a slide coming up, they're all related to one another in a specific way. So on the far left, we have the Kafka producer consumer API. These allow you to do whatever you want in pretty much any programming language, with the downside being that you have to implement all that code. Kafka Streams builds on top of the Kafka producer consumer API by wrapping up a lot of the common stream processing problems with a simple library that you can use to ultimately reduce the amount of code that you have to write for your stream processing jobs. And then finally on the right, we have ksqlDB, which actually wraps up Kafka Streams. And instead of requiring you to implement code using the Kafka Streams library, you can define stream processing jobs without writing any application code at all by just specifying your processing logic using SQL. And as I mentioned, each of these approaches are fundamentally related in that they actually build on one another. So at the very core of all of these stream processing approaches, we have the Kafka producer consumer API, and the Kafka Streams library wraps around the Kafka producer consumer API. And the stream processing jobs that you implement using the Kafka Streams library essentially compile down into producer consumer API code, with the benefit being that you don't have to write any of that code. It gets compiled down in a very robust, efficient way based on the logic within Kafka Streams. And then finally, we have ksqlDB, which uses Kafka Streams as its foundation. So each continuous SQL query that you specify with ksqlDB actually compiles down into Kafka Streams bytecode, which obviously, again, in turn compiles down into Kafka producer consumer code. So the key thing about this technology organization is that any of the benefits introduced within a layer beneath one layer are automatically inherited by the layer above. So for example, if any improvements, whether they be stability or performance improvements, are made to the producer consumer API, that automatically translates into Kafka Streams as well. So all of the benefits from the layers beneath are inherited upward to the layer above. So the key thing about this organization is that the foundation is rock solid. Kafka Streams is extremely battle tested. The producer consumer API has been around even longer, so it's even more battle tested. So that is the foundation that's being leveraged by ksqlDB. And this slide here illustrates, I think in a kind of visceral way, the key differences between each of these three stream processing approaches. So each thing that I'm going to show you on this slide actually solves the same problem. What this code is doing here on the left is it's simply counting up the number of records seen for a given Kafka message key. So fairly straightforward, very simple workload. And as you can see here, there's actually quite a bit of code to solve that relatively simple problem. And then as we move over to the right, the same problem is being solved here, obviously with significantly less code, illustrating the benefits of leveraging the Kafka Streams library to abstract away a lot of the producer consumer code beneath it. And then all the way on the right, we have the simplest, most succinct example here, where this same problem, counting events by key, is accomplished using just a very simple canonical one-line SQL query. So to dig into the pros and cons of each approach, one thing I'll say is that none of these approaches is necessarily better than the others. I think you should use whichever one is best suited for your specific workload. So I'd like to highlight some of the pros and cons of each approach here to help you think through which one might be the best. for you. So starting all the way over on the left with the producer consumer API, the benefit of this approach is that you have full control, maximum flexibility, because you're ultimately implementing this code yourself. So it can be whatever you want it to be. It's just application code, and you can use pretty much any client or any Kafka client that's out there, which is basically every major programming language out there nowadays has support for the producer consumer API. So you can have full control over the code and use whatever programming language you want essentially for this approach. With the downsides being that, as I mentioned before, you have to write all this code. It's all up to you. There are no primitives that you can use to solve some of the really common stream processing problems that we've seen. And also the deployment and operational models are essentially up to you. So if you have stream processing logic implemented with the producer consumer API, you have to deploy that however best suits your organization. So moving over to Kafka Streams. Kafka Streams is in many ways a good balance between the producer consumer API versus ksqlDB. So you still get quite a bit of control over the code because it's still just code. And the other thing that's really good about this approach is that it includes support for doing like pretty much any common stream processing sort of task that you would need, all wrapped up in a library that's really easy to use and is as simple as possible and very battle hardened. In terms of cons, similarly to the producer consumer API approach, the deployment model for Kafka Streams applications is also up to you. So Kafka Streams stream processing jobs run as regular binaries. So if you implement a Kafka Streams application in Java, that's just a compiled Java application that you run like any other Java program. So that's ultimately up to you. And also, if you make any changes to your workload, you have to do a full redeployment of your Kafka Streams application. You can't make runtime changes to the application, which is actually true for the producer consumer API also. And as of now, Kafka Streams applications have to be implemented in some JVM supporting language. So they leverage the JVM, so that may be a limitation for some organizations. And so finally, for ksqlDB, I think probably the biggest, most generally useful benefit of ksqlDB is that no application code is required. So any stream processing logic you want to define can be defined fully within SQL. All the compilation down into Kafka Streams bytecode happens transparently. You don't have to worry about any of that. And not only is SQL typically a little bit easier for organizations to use, especially larger organizations, most of which have expertise in SQL nowadays, it's also very succinct. So as you saw on the previous slide, the ksqlDB approach to solving the problem on that slide was just a simple one-liner. So it's easier to write SQL, and SQL is actually significantly shorter or more succinct and less complex than the equivalent bytecode. ksqlDB also offers less operational overhead than each of the other two approaches. ksqlDB runs as a cluster of servers, much like other data processing systems, and you can just issue SQL statements to that server as your workload changes and evolves over time without having to restart anything. You don't have to restart ksqlDB nodes. You don't have to redeploy everything. You can just issue SQL statements as the servers are running and just let them continue to run. And finally, I kind of alluded to this a little bit, but ksqlDB, as of recently, supports online schema upgrades for certain changes. So this allows you to actually make changes and evolve your continuous stream processing logic without having to bring ksqlDB down. So not just create new stream processing logic and submit new queries, but you can actually alter existing queries while they're running without having to bring anything down, which is a pretty big benefit operationally. As far as the cons of using ksql, I think the biggest and most obvious one is probably that it's not the right tool for the job if your stream processing logic does not fit into the confines of SQL. There's typically no reason to force a workload into SQL if you really want to use ksqlDB. In some cases, it would be better to just use native code using either Kafka Streams or the producer consumer API if you can express your logic with SQL. And if you do want to extend SQL ksqlDB does support the implementation of user-defined functions. So these are functions you could implement in Java and then call them from within your SQL queries. You can do that, but it's not straightforward and requires a little bit of expertise. And obviously you have to know how to write Java code as well. So that was a high-level overview and background around why we built ksqlDB, how it compares to the other approaches. Now we're going to focus on ksqlDB specifically and drill into some of what I believe are the more unique properties that it has. And then after that, we'll dig into the architecture and internals a little bit. So previous slide kind of demonstrated the complexity that a lot of modern data infrastructures can take on. This slide here is showing a relatively typical stream processing architecture. So even if you are doing stream processing, a lot of approaches that you could use are actually still relatively complex in that they require the usage of numerous systems all cooperating together. For example, if you want to query the output of a continuous SQL query or a continuous stream processing job, in many approaches, you have to route that output out to a database that you can then query and things like that. So a lot of stream processing architectures are still relatively complex. And one of the biggest aims of ksqlDB is architectural simplification. So rather than assuming that users will be comfortable deploying all these disparate systems and operationalizing them and monitoring them in production, we try to really bring in all of the common stream processing functionality underneath a single unified product, and that's ksqlDB. So as you can see here, you have state stores, which we'll get into a little bit later, but those allow you to store the incremental output of continuous views, basically materialized views. You can have connectors, which bring in data from external systems and also route data out to external systems. You can create those sorts of connections entirely within ksqlDB. And then, of course, the core stream processing logic is really the focus of ksqlDB. But again, the idea here is architectural simplification. That's one of the primary aims that ksqlDB has. So this is a typical architectural diagram of a relatively simple stream processing architecture. At the bottom in the center here, that's Kafka. You may be using Connect to integrate with external sources and sinks. Kafka Stream sits on top of all of that to provide continuous processing. And then you can layer ksqlDB on top of that so that you only ultimately have to interact with a single system. So as I mentioned before, ksqlDB aims to serve as a entirely unified interface over your entire Kafka infrastructure. So you don't have to worry about interacting with any of these other systems. You can just interact with ksqlDB as your primary mode of interaction with your stream processing infrastructure. In terms of the deployment model for ksqlDB, what is a ksqlDB cluster? It's essentially a cluster of nodes. Each of those nodes is running the ksqlDB server. And one of the key design properties of ksqlDB is that it uses Kafka for all data interchange. So ksqlDB nodes in a cluster generally do not communicate directly with one another. And this is a very conscious design decision that we made because once you have nodes that begin communicating with one another, you essentially end up re-implementing something like Kafka as a reliable message queue to make sure all of the data gets between the nodes that are communicating. We elected not to do that. We want to leverage all of the functionality of Kafka that already exists, as well as its battle-hardened history, so that we don't have to re-implement any sort of reliable queuing or inter-node communication mechanisms. So this is a really important design decision, and what it ultimately amounts to is that ksqlDB inherits its distributed systems primitives from Kafka, which again is very battle-hardened. It's been around for a long time, super solid. And so we saw no reason not to leverage that as a foundation. And each of these nodes has one key configuration property that makes them into a single unified cluster. And that is this property you see here, the KSQL service ID. Any nodes configured with the same service ID will act as one cluster. So if you want to bring up a new node and add it to this cluster, you can spin up a node, run ksqlDB on it, and as long as you configure it to use a service ID of the existing cluster, it will join that cluster. And as far as interacting with this cluster, each node in this cluster exposes an HTTP endpoint, which clients can connect to. So you can use the pre-built CLI, you can use the UI if you're using Confluent's cloud offering. You can also use the HTTP API directly, meaning you can do this from any programming language you want. And then SQL statements are submitted over those connections to those HTTP endpoints in order to issue SQL queries and other SQL statements to your ksqlDB cluster. And here's just a quick example of what that actually looks like. So this command up here, we're running the pre-built ksqlDB CLI that's included with KSQL, passing a username and password, and then an endpoint here. Once that connection is made, I'll be dropped into an interactive shell that behaves just like an interactive shell behaves with any other SQL database. And then I can issue queries, whatever queries I want. Here's an example of a query looking up a value in a materialized view. So that's the cluster model and how nodes interact with one another. The last thing I'll mention here is that any node in a ksqlDB cluster clients can connect to that node. They're all essentially equivalent. So you can connect to whatever node you want. The result will be the same after your query is submitted. In a lot of cases, users put this cluster behind a load balancer so that the load balancer just has a single endpoint that your clients can always connect to that will always be there. And then the load balancer will just randomly assign the request to any of these nodes, since any node can process any request. So it's a pretty simple deployment model. So now we're going to drill into a little bit more detail about what a ksqlDB workload is. I think most workloads fall into four, or all of the components of a given ksqlDB workload typically fall into four categories that I'm going to cover here. Starting with integration. So if you want to do stream processing, you need some data. You could be writing that data into Kafka directly. But in a lot of cases, especially in more complex data infrastructures, there will be a number of external data sources and sinks, and you want to pull that data into KSQL to do processing on it, or push the result of continuous processing out to these kinds of external databases. So that's the first component of a typical ksqlDB workload. The next component, this is definitely the core component of a stream processing workload, and this is where you continuously apply the business logic as defined by your SQL queries. So these can be anything like transformations. If you want to, perform a string transformation on a specific column in your data, if you want to join topic data from multiple topics together into unified events to simplify downstream data processing, that would fall under this category. So this is the real core stream processing logic. And then another category here that we're increasingly seeing is materialized views. So rather than just pushing out the results of your continuous processing from the category above, you may just want to maintain continuously updated incremental materialized views that you can then query to check the point in time result of a particular streaming computation. And materialized views are much like materialized views in any other traditional SQL database. They basically behave as a table, and you can look up the results from that table whenever you want, whenever you'd like, to get the point in time result, rather than getting the streaming continuous incremental result of a streaming query, which isn't always necessary, as I'll cover in a later slide. And then the final category here kind of relates to the one above. This is where you're doing on-demand lookups against the materialized views maintained in the category above. So the continuous SQL queries that maintain materialized views in ksqlDB, they just run forever. As new data comes in, they will incrementally update the underlying materialized view with the latest value, and then lookups allow you to get the result of that value at any point you want. And these queries again, behave much like they would with a regular SQL database. You just issue the query and you get a result back. It's a request response model. We think that's still extremely valuable. And the final thing I'll note here is that ksqlDB aims to provide enough functionality and support for all of these categories under one unified product. So all of these things you can do with ksqlDB, and all of these things will be involved in most non-trivial stream processing workloads. So again, unification is really the goal here. I'd like to briefly run through all of the key abstractions that you can leverage that are offered by ksqlDB. So everything you see here can be invoked within a SQL query. So starting at the very top, we have connectors, which integrate with external data sources and sinks. You can configure those external connections using SQL with ksqlDB. Those ultimately leverage Kafka Connect internally. So any connectors that you can use with Kafka Connect, you can actually configure them to run from ksqlDB directly without having to worry about how to manage, deploy, or operate Kafka Connect. And then another key concept is joins. So ksqlDB has really rich support for streaming joins, which ultimately allow you to join together data from multiple Kafka topics, which is pretty valuable. Typically, we see joins as a means to amplify the value of a lot of data sets. When you can join together multiple disparate data sets, the resulting data set is synergistic in a lot of cases. And joins with ksqlDB allow you to achieve that using SQL. And then we have aggregations. These are things like counting the number of rows for a given key, as we saw in a previous slide, computing the standard deviation over a column within a given Kafka topic, taking the average of a given column, things like that. ksqlDB has rich support for pretty much all of the common aggregations that you would need in a lot of the aggregations you would see in a traditional SQL database. We also have filtering. So this is very, very useful in the context of stream processing. To frame this in terms of SQL, this is basically just a where clause. So where clauses allow you to filter data based on some criteria. Like the example here is running a continuous query that selects HTTP response events that only have a status code of greater than 500 if I want to create a stream of error responses for whatever application is producing that data. Filters are very, very useful for that kind of thing. Transformations are also another important category. This is where you would do basically like any sort of expression execute any sort of expression on top of topic data. Like if I want to extract a string from a string using a regex, I can do that. That's a transformation. If I want to put two columns into an arithmetic expression, like I want to add them together, that's a transformation. So all of that kind of stuff is very, very easy to do with ksqlDB and will be central to most stream processing workloads. And then finally, we offer a pretty large suite of built-in functions. In the regex example I used in the step above, we have a bunch of regex built-in functions for regex processing. We have string manipulation functions. We have some geospatial functions. All of that kind of stuff you can use out of the box using built-in functions that are called from directly within your SQL queries. And so going back to the previous four categories, I just wanted to quickly run through what an actual example would look like for each of these stages. So the stage here at the top, this is what it looks like to create a connector. So you have the create source connector syntax, you can name it whatever you want. And then this is all the configuration that ultimately gets passed to a Kafka Connect connector. So I omitted some of the key values here for the sake of brevity, but it's essentially just a bunch of key value configuration parameters that you want your connector to use. Once you do that, this connector will begin running and you will have data from that source coming into a Kafka topic. That topic you can then leverage or reference directly within any SQL queries you're writing within ksqlDB. So this is an example of a relatively simple transformation. We have a stream of page views events. As you can see here, we're selecting 3 columns out of that stream of page view events, and we're applying a simple transformation to a timestamp field. So what we're doing here is we're basically formatting it based on a format string that we specify. Very simple, but as I mentioned before, transformations can be a broad variety of things. This is just a canonical example of what the actual syntax looks like. And then this syntax you see here is how you would generate a materialized view. So you can see we use create table syntax because the result of this continuous query will create a stateful table that is stored on each ksqlDB node, depending on what your partitioning scheme is. Each node will have some subset of the overall state used to maintain this materialized view. And what we're doing here is we're basically aggregating a stream of purchase events on the country dimension. So what this is saying is for each country, how many orders have I received? And another thing that's important to note here is that this is actually a window-based aggregation. So this won't just aggregate on the country dimension, it will actually have a time bucket as well. So the final result of this materialized view is for each country, how many orders did they receive within every 5-minute window of the time period that this persistent query has been running for. And then finally, we are querying the above materialized view using what we call a pull query because you're pulling data out of a materialized view in a request response model. This is targeting the number of purchases that have been made with the country code USA. And because I'm not specifying a time window here, what I'll get back here with this query result is all the time buckets since the query began running for the country with the code USA. So you'll have one row for each 5-minute bucket. So this query could potentially return many rows. And I'd also like to emphasize that these two stages are actually one of the things that make ksqlDB very unique. A lot of other stream processing offerings take the approach of assuming that you can use an external data store to support things like materialized views. So rather than maintaining a materialized view directly within the cluster, you would pipe out all of the incremental changes being made to that underlying materialized view to a data store that you could then query, like Postgres or Oracle, whatever. That would just be a stream of updates to those databases, and then clients would connect to that database if they wanted to do a query like this. So with ksqlDB, no external data stores are needed. You can do all of these things directly against ksqlDB without having to worry about operationalizing another database, which is really nice because you just have one API, one endpoint, one query language, which is just SQL, one system. So again, simplicity is really the goal here. And so in the previous slide, I mentioned the concept of pull queries briefly. And the reason I think pull queries are really important to ksqlDB is that traditional stream processing, what I'm calling pure stream processing in this case, is not enough for many workloads. You still have a need for the request response type queries, like we saw in the previous slide, and that's totally fine. That request response model is still extremely useful, and so we ultimately harmonize both of these key query forms underneath one single interface. So I alluded to the pull queries already. That's when you're pulling data out of a materialized view using a request response model. And the other query form is called a push query, which is a streaming query. So these queries are also written with just regular SQL. They run forever or until you terminate them, and they continuously output an incremental stream of changes representing how the data is changing in the underlying query, or for the data set that the underlying query is processing. So push queries push data out of ksqlDB to clients, a stream of incremental results. Pull queries pull data out of ksqlDB using the request response model. Pretty much all complex stream processing workloads that we've seen use both of these query models. But again, for queries similar to pull queries, request response type of queries, most users or organizations are using a separate data store if they're not using ksqlDB. So we harmonize both of these query forms underneath one single unified interface because we think they're actually both still really important and both very, very useful. And I kind of mentioned this a little bit already, but I think a good way to think about ksqlDB is in terms of this push-pull duality. I think it really captures the essence of ksqlDB in terms of how we aim to unify stream processing workloads underneath a single interface. As I said, we think both of these query forms are very important, and so we put them into the same product so that you can use each query form however you want without having to deploy and operationalize multiple systems. So the last couple slides here, before we quickly get into some architecture and internal stuff, I just wanted to point out a couple of features that I think are really unique to ksqlDB. I mentioned this briefly early on in the presentation, but one of the really nice things about ksqlDB is that it has support for online schema upgrades. Meaning if you have a stream processing workload running, which you have implemented using SQL queries with ksqlDB, and you want to, for example, add a column to a continuous query. Before we had this feature, you would have to drop the query and recreate it and have the new version read from the beginning of time to catch up, which is obviously not ideal. And then in other systems like Kafka Streams, you would actually have to take the Kafka Streams application down, make your changes, recompile it, and then bring it back up. With ksqlDB, you can modify persistent queries, streams, and tables using create and replace syntax or alter syntax. And the really nice thing about this capability is that when you make a change to a persistent query that's been running continuously, the change will take effect and the persistent query will begin reading from wherever the previous version of the continuous query left off, which is really nice. As I mentioned in previous releases of ksqlDB, when this wasn't supported, you kind of had to manage that yourself. You could either write a custom application that populated the new version beginning at the right offset, or you could read from the beginning of time, neither of which is ideal. With the latest version of ksqlDB, you can actually just run create or replace syntax to update a continuous query, and then it will begin reading from wherever the last one left off so that no messages are dropped, which is really nice. And again, very unique capability when it comes to stream processing tools. And this schema modification functionality is actually wrapped up in a migrations tool. So you can run create or replace syntax directly using whatever ksqlDB interface you want, whether it's the CLI or the HTTP interface. You can also use this migrations tooling, and this migrations tooling works much like migrations work in a traditional database. So this command here is creating a new migration. That creates an empty file. It's a SQL file, and I would put my workload modification statements within that file. And then I would run the ksql migrations apply command to apply that migration to the target ksqlDB cluster. And after that point, the cluster's schema will be upgraded. Here it's upgraded to version 2. If I tried to apply the same migration again, it would essentially be a no-op because the ksqlDB cluster already knows it's on schema version 2. So the important thing here is that these behave much like database migrations work with traditional databases, which is really nice. Another thing that I think makes ksqlDB really unique is that we have support for Lambda functions. So what Lambda functions allow you to do is specify a SQL expression that is then applied to a collection type. So what this capability ultimately does is it allows you to somewhat extend the base functionality of ksqlDB, but you don't have to go through the process of implementing user-defined functions in Java. You can just use Lambda functions themselves. And that's actually one of the key reasons why we decided to build this, because we realized that a lot of the user-defined functions that customers and users were implementing could be solved using Lambda functions. So just to go through, I'll go through the top example here. We have an array of strings as the input. And this is the Lambda function. So S means each element of the array. This function will get applied to each element of the array. And here we're applying the uppercase built-in function. So what this expression will ultimately output is an array of uppercased strings. So relatively simple transformation. It's important to note that what can be in these Lambda function bodies is essentially any SQL expression that you could use in a select query. So they're pretty powerful. So that wraps up the background and overview. I'd like to take a couple of minutes to go through some of the internals. I think we're running a little bit short on time. We could also go through a couple of example use cases. Chad, do you have any preference for which we cover? I don't know if we'll have time for both.
Yeah, just real quick, I want to make mention too, for whatever reason, when I set this up, I did not allow participation, the chat function. If you guys have questions, please email me at chad@trilogyit.com. That's chad@trilogyit.com. Just email me your questions and I can get them over. If it's afterwards, I'll make sure to get that over to Derek. But yeah, anyway. If you'd like to go over some use cases, I feel like that'd be really helpful. Since people weren't able to ask their questions, I actually do have one question for you, but do you want to save that for after what you're about to talk about?
Sure. Yeah, let me bring up the use cases here.
Great. Yeah, and that way people can send their questions too. If you follow us on Twitter, it's Trilogy Innov Inc. So INNOVINC. If you want to tweet your question as well. So whatever works best, chad@trilogyit.com or Trilogy Innov Inc. on Twitter. So, all right, Derek, I'll give it back to you here.
Cool. So we already saw some relatively straightforward SQL examples in previous slides. I'd like to frame those around actual use cases now. So we have 3 core buckets of use cases. The first bucket is what we call streaming ETL, streaming, extract, transform, load. ETL is a term that largely corresponds to legacy kind of batch jobs where you're extracting data from some data source, providing or performing a bunch of transformations on it, and then loading it into a new data source. ksqlDB allows you to do that in a streaming real-time fashion. And this is probably the core of most of our workloads. Most workloads are using things and features beyond just streaming ETL, but the core problems that many users are solving would be centered around streaming ETL. So this example here, very simple example here, I'll just run through each of the stages. So at the top, we have a connector being created. So this connector is configuring an external connection to a MongoDB database as a data source. So once this connector statement is run, data from this MongoDB source will be coming into ksqlDB as configured by this connector, which means I can then perform processing on it. Before I need to do processing on the stream of data coming in from MongoDB, I need to apply a schema to the topic that this results in. So that's what this statement right here is doing. It's applying an Avro schema that already exists to this MongoDB source data, which is stored in this topic here. And this topic would have been configured as one of the options up here. As I mentioned before, I just didn't want to include every single option for the sake of brevity. And finally, once I have a schema applied to that data coming in from MongoDB, I can write any continuous SQL queries I want on it. Here, what we're doing is we are joining this incoming stream of MongoDB data with a customers table. This is a very common pattern we see in a lot of ksqlDB workloads where users have mostly static tables, static meaning they change infrequently. Like in this example, the customers table would be a static table. So this table has a customer ID followed by all of the different fields associated with that customer, whether they be things like first name, last name, their age, birthday, whatever you want in there. We can join on that kind of static data to include it into the streaming output of this query to make it easier for downstream processing. They already have all those fields that they need rather than having to look them up at that level. The second use case bucket is what we call materialized cache. So this is centered around the materialized view functionality that I've been talking about during this presentation, where you are doing things like aggregating Kafka topics and storing that result persistently. So what we have up here is a relatively simple materialized view. It is computing the number of unique users seen within a stream of page view events, also the number of all page view events on the URL dimension. So for each URL, how many uniques have I seen and how many total requests have I seen? And this is also using an hour. So these aggregations will be performed at the hourly level. So you'll have for each URL and hour, how many uniques, how many requests. And what we're doing here is we're looking up some data from the above materialized view. So this is just a standard select query, looks exactly the same as a select query would look in most databases. It's targeting a specific URL, and it's also targeting a specific time range. So this is querying 1 day of data. Since we're aggregating by hour, we'll get 24 rows back here. So all of the hours associated with this URL will be returned, and then the query will be done. It's a request response query, much like a regular database. And then just another simple example, we're selecting all of the events for the same URL with no time qualifier. So this will just return data for all the time buckets that exist in that materialized view. And then finally, we have the microservices bucket. And what we see users doing with this bucket is using ksqlDB to perform processing in a centralized location to consolidate communication between a bunch of different microservices. So rather than each microservice in a microservice architecture having to do all of the right processing itself or know what processing to apply, all of that is done by ksqlDB itself. And then each microservice just gets pushed all of the events that it's interested in. It can also subscribe to all the events that it's interested in based on or by running a continuous SQL query using things like the filter mechanisms that I mentioned in a previous slide. So again, the core idea here is to consolidate processing between a large collection of microservices so that each microservice is just pushed all of the data that it's interested in. So in this example, we have a stream of transactions. We have some basic data you'd see in a stream of transactions like transaction ID and email address, credit card number. And this query here is powering a fraud detection microservice. So to break down this query a little bit, what we're doing here is we are counting the number of failed transactions from a stream of transactions on the card number dimensionality. And what we're doing with this aggregation is we're making the assumption that any failed transactions, any more than 3 failed transactions within a 30-second window, we flag that event or that transaction as fraudulent because of that criteria. And then this will be pushing its results out to a stream called fraud alerts, which the fraud processing microservice can subscribe to downstream and do something with that data as it's pushed fraudulent alerts. So it could do things like if I get a fraud notification for a given card, deactivate that user's account temporarily, something like that. It can do whatever it wants. But the key thing is that it's only getting the data that it is interested in, which is transactions that are flagged as fraudulent. Cool, Chad. So that's it. I think we can use the rest of the time for questions or discussion. I know you said the chat's not enabled, but if you received any questions, I'd be happy to answer them.
Yes, did get one question and is around any best practices around performance optimization.
Yes, definitely. So this is a very common question we get. If you look in our docs, which are located at docs.ksqldb.io, there is a performance guidelines document that will break down all of the key performance critical areas of ksqlDB and provide advice around how to make your workload most efficient and avoid inefficient queries or other undesirable behaviors. So that will break down pretty much everything you could think of, and it will illustrate all the best practices around each performance sensitive area.
Great. And is there a way to get started easily? I know that Kundan and I believe the first presenter Andrew had provided some links and everything, but is there a way to easily get started with this stuff for folks that are looking to kind of play around with this?
Yeah, definitely. Thanks for asking that question. So this is the ksqldb.io site that I'm showing here. This get started button will take you to a quick start, and this quick start will describe how to get started with any distribution of ksqlDB. So let me break these down really quickly. So the standalone release is a community release that's released independently of Confluent or the Confluent platform releases. And you can get that distribution via Docker. You can get it as a Debian package. You can get it as an RPM package or as a tarball. And depending on which option you select here, it will generate the steps for you within this quick start guide. So that all you need to do is copy and paste these, and within a couple of minutes, you'll have a ksqlDB environment running locally. If you have Docker, Docker is probably the easiest way because you don't need to install anything. You can just run this Docker compose file here that we provide for you, run Docker compose up, and then your entire environment will essentially be running. But again, we have other packages as well if you'd like to install Debian or RPM or tarballs. If you'd like to try our cloud offering, that's also laid out here. All the steps required to do that are provided for you. That's also one of the easiest ways to try ksqlDB. It's just fully managed. You don't have to worry about running or managing the infrastructure. You just sign up, click on create application, and it will be running for you in a couple minutes. And then this category is Confluent Platform, which is our enterprise distribution, which packages up the standalone releases from ksqlDB. So ksqldb.io, go to the quick start. You should be able to find anything you need.
Great. Yeah, and I'll be sure to make send everybody links to this stuff and reference anything that that Derek put together, so we can talk about that offline, Derek, and then I'll get that emailed out to everybody. So, yeah. Also curious, you and I were talking kind of in the beginning of if there's anybody in the audience that could potentially have pain points that they're currently experiencing with the technology they're currently using or evaluating. So if you guys have questions or a use case you could send over to me, we'd be curious to see what you have and get the discussion going, and maybe we can have a follow-up talk. So yeah.
Yeah, absolutely. We're always eager to get feedback or information around pain points people are experiencing, even if they're not using ksqlDB. Pain points with whatever approach they're currently using. Please feel free to send those to chat, and we'll help address those for you.
Excellent. All right. Well, I know we're running up on time here. I didn't have any more questions come through, but again, if you guys have follow-up questions, I'll make sure to get them over. So, Derek, thank you so much. It was really great to hear all this. I hope everybody got a lot of great value out of it. As I said before, we're going to continue this series. Probably take a little bit of a break. We've had 3 back-to-back every 2 weeks. So. We'll be sure to get some more content out for you. So if you guys have feedback, let us know. I'll be sure to get Derek out there as well. All the info and references that he discussed, and we'll have this recording on YouTube as well later on. So thank you all so much for joining us, Derek. Thanks so much for joining and taking the time out of your day. Really appreciate it for sure.
Yeah, thanks for hosting and organizing, Chad. Happy to be here.
Absolutely. All right, take care, everybody.
Cool. Bye.
See you, Derek. I hope you enjoyed this episode. Please don't forget to like, subscribe, and share.